All right, today we're going to pull back the curtain on one of the most important components in all of electronics, the inductor. Now, at first glance, it's really just a simple coil of wire. But don't let that fool you. It has this fascinating, almost magical property that makes our entire digital world work. So let's dive in. And I'm not kidding when I say these things are everywhere. I mean, just look around you. They come in all sorts of shapes and sizes, and they are absolutely critical players inside pretty much every circuit that powers your life. We're talking everything from those tiny little components on a motherboard to the big, beefy ones you'll find in a power supply. They are essential. So what is their deal? What's their main job? Well, they have this one unique superpower. This classic circuit diagram shows it perfectly. An inductor can actually keep a light bulb lit for just a moment after the switch is opened. Think about that. It does this because it fundamentally resists any change in the flow of current. But how? Well, that's what we're here to find out. So here's the game plan. First, we're going to explore that core superpower. Then we'll get into the physics of its voltage-current relationship, crack one open to see what's inside, figure out how its strength is calculated, and finally, we'll tie it all together to see why it's so darn important. All right, let's get right to it. What is this component's defining characteristic? What makes it so special? Okay, so at its heart, an inductor is what we call a passive component. That just means it doesn't create new energy. Instead, what it does is it temporarily stores energy in a magnetic field. And then it uses that stored energy to put up a fight against any sudden increase or decrease in the electrical current that's trying to flow through it. You know, a really great way to get your head around this is with an analogy from the physical world. Just imagine a big, heavy flywheel. It takes a lot of effort to get it spinning, right? And once it's going, it really doesn't want to stop. It has inertia. Well, an inductor is basically the electrical version of that flywheel. It just hates any change in the flow of electrons.
Okay, so we've got a handle on what it does. Now let's get into the how. I mean, how does this simple little component actually manage to push back against the flow of electricity? This is where it gets really interesting.
And that's a fair question, right? It's just a coil of wire. How can it possibly have such a huge effect on a circuit? Well, the answer lies in an invisible force that you're probably already familiar with. So whenever current flows through that wire, it generates a magnetic field that wraps around the coil. And this field is where all the magic happens. This is where the inductor stores its energy. It's not really the current itself that's the key, but what happens when that current, and by extension the magnetic field, tries to change. And this is the most important part, the absolute core concept. When the current changes, the magnetic field has to change with it. And according to the laws of physics, a changing magnetic field actually creates or induces a voltage. And this new voltage pushes back in the exact opposite direction of the change, desperately trying to keep the current nice and stable. And this whole behavior is captured perfectly in one really elegant equation. V equals L times di over dt. Now, V is the voltage that the inductor creates to push back. L is the inductance, which is just a number telling us how strong the inductor is. And that di over dt part, that's just a fancy way of saying how fast is the current changing. So let's think about that for a second. What happens if you have a steady, direct current, like from a battery? Well, the current is constant, so it's not changing. That means our di dt term is zero. And anything times zero is zero. The induced voltage disappears. The inductor basically goes to sleep. It doesn't resist at all and just acts like a plain old piece of wire. It only wakes up and fights back when that current tries to change. Okay, we've covered the theory. Now let's get our hands dirty and actually look at what these components are made of. Let's crack one open. You know, it really boils down to two main parts. You've got the winding, which is usually some insulated copper wire, and then you have the core, which is the material that the wire is wrapped around. And let me tell you, the choice of what that core is made of is incredibly important. So the core can be made of a non-magnetic material, like ceramic. In this case, it's basically just there to provide a form for the coil to wrap around. We often call these air core inductors, and they're great for high-frequency applications. Or the core can be magnetic, using materials like iron or ferrite. These materials are like an amplifier for the magnetic field, allowing you to get much, much higher inductance values in a much smaller package. And it's not just the material. The shape of that core plays a huge role too. A toroidal or donut-shaped core is super efficient because its magnetic field is almost completely trapped inside the core itself. Then you've got other shapes, like an E-core, which can be designed with a tiny air gap to stop the core from getting overwhelmed or magnetically saturated at high currents.
So we know an inductor's ability to resist change depends on how it's built. But how do we actually measure that? How do we put a number on that ability?
Well, that property is called inductance, and we use the letter L for it, like we saw in the equation. It's measured in a unit called the Henry. So 1 Henry is just the amount of inductance that gives you 1 volt of pushback when the current is changing at a rate of 1 amp per second. And this shows us that inductance isn't just some abstract idea. It's a direct result of the inductor's physical design. The more turns of wire you have, the larger the area of the coil, and the better your core material is at focusing that magnetic field, the higher the inductance is going to be. At the end of the day, it's all about geometry. Okay, we've gone through the what, the how, and the why of the physics. Now let's bring it all back home. Why is this little component so incredibly vital to everything we do? Let's just recap the big ideas. Inductors store energy. They fight any change in current. They let steady DC sail right through, but they put up a fight against changing AC. This split personality is exactly what makes them so unbelievably useful. In power supplies, for example, they're the ones responsible for smoothing out choppy electricity, making sure clean, stable power gets to your sensitive electronics. In filters, they're the bouncers, blocking unwanted high-frequency noise. So, I'm gonna leave you with this final thought. If an inductor's whole job is to smooth things out and resist sudden change, where in our chaotic, noisy, high-speed digital world do you think that ability is most critical? Well, as we've seen, the answer is pretty much everywhere. Thanks for watching.
Let's study more and like, share, and subscribe for such more content. And comment something you want to learn.